Right now in your kitchen, you have enough materials to generate free electricity from the sun. I'm not talking about silicon panels that cost thousands of euros and that big electric companies have spent decades selling to you as the only possible option. I'm talking about something completely different, something you can build this afternoon that fits in the palm of your hand and actually works. This is the experiment. What you're seeing here is a homemade photovoltaic cell built with aluminum foil, vinegar, salt, and an empty soda can. No silicon, no laboratory semiconductors, no 4-digit bills. The result is not going to power your entire house. That would be lying to you. But it is going to prove something that university textbooks have been explaining for more than a century. And that the energy industry prefers you never connect with your daily life. The photovoltaic effect is not expensive magic. It is chemistry, and chemistry is in your pantry. Before I explain how to build it, I need you to understand why you have never heard about this before. Because that answer explains everything. If this kind of knowledge seems valuable to you, subscribe to the channel now and activate the bell. Every week we publish what nobody else dares to teach. Leave a like if you want the algorithm to show this to more people. In 1839, a 19-year-old French physicist named Edmond Becquerel discovered something extraordinary while experimenting with electrolytes in his laboratory. When he exposed certain materials to light, they generated electricity. He called it the photovoltaic effect. He was 19 years old. It was 1839. 186 years later, the average price of a residential solar panel system in Spain ranges from $8,000 to $15,000, depending on the installed capacity. The technology that generates that electricity is essentially the same one that Becquerel discovered in that laboratory in Simononico. What has changed is not the principle. What has changed is who controls the production, the profit margins, and the narrative. I'm not telling you there's a cinematic conspiracy. I'm telling you something more ordinary and more disturbing. When an industry is worth trillions of euros, it has every incentive in the world to make sure its expensive solution is the only one you know about. Commercial solar panels exist because they are scalable, efficient, and profitable for the companies that manufacture them. Homemade photovoltaic cells exist because physics does not care about business interests. And here's the fact that should make you the most uncomfortable. The simplified version of this process is taught in technical universities all over the world. It is not a secret. It is in the manuals. It's simply that nobody has had any interest in translating it into the language of an afternoon DIY project. Until now. The photovoltaic effect happens when a photon, a particle of light, strikes certain materials and releases an electron. That released electron can be captured and conducted through a circuit. That is electricity. Essentially, the entire solar industry on the planet is based on that single idea. Commercial panels use doped silicon, a semiconductor material processed in high-tech factories that require clean room conditions, controlled temperatures, and complex industrial processes. That is what justifies the price. But silicon is not the only material capable of exhibiting the photovoltaic effect. Cuprous oxide, which is simply oxidized copper, is a natural semiconductor that generates electricity when exposed to light. And copper? Of course, you can get it at any hardware store for a few cents. The controlled oxidation process that converts metallic copper into cuprous oxide does not require any special equipment. You only need heat, time, and patience. The cell you're going to build uses that principle. It is a modernized Becquerel cell, a version of the original 19th century experiment adapted with materials you can buy this very afternoon. The performance is much lower than a commercial panel, approximately between 0.1% and 0.5% efficiency compared to the 20% to 22% efficiency of modern panels. But to understand the principle, to prove to yourself that this really works, it is more than enough. One copper sheet. About the size of an A4 paper, you can find it in hardware stores or art supply stores as engraving sheet metal. The cost is around $2 or $3. Common kitchen salt, the table salt you already have at home. You do not need anything special. White vinegar or saturated salt water, either one works as the electrolyte. If you already have vinegar in your kitchen, you spend nothing. A transparent plastic container, such as a food container or a reused jar. Transparent is better because you will be able to see the process. Fine grit sandpaper, 220 grit or higher, to prepare the copper surface. Conductive wires with alligator clips, the same ones used in basic electronics experiments. You can find them in electronics stores for less than $2. A basic multimeter to measure the generated current. If you don't have one, there are ones for $5 or $6 in any bazaar or electronics store. You can also use a smartphone application connected to a sensor, although the multimeter gives more reliable readings. A heat source, your kitchen burner, that's all. Total cost if you start from scratch, between $5 and $10. If you already have some of these materials at home, probably less than $5. And before you get to the assembly part, there is a previous step in the oxidation process that most tutorials omit, and that is exactly the reason why many fail. Stay, because that detail changes everything. First, cut the copper sheet into 2 equal pieces, approximately the size of your hand. Sand one of the 2 pieces with the sandpaper until the surface is clean, without oxide marks or dirt. The copper must shine. This step is important. Surface dirt interferes with the homogeneous formation of cuprous oxide and reduces the performance of the cell. Second, place that sanded piece on the kitchen burner over medium-high heat. In a few minutes, you will see the copper begin to darken. It will pass through orange, red, violet, and finally black tones. The black color is copper oxide Cu₂O, which is not what you are looking for. What you are looking for is cuprous oxide Cu₂O, which appears in reddish or brick-colored tones beneath the black layer. Here's the step nobody tells you. Let the copper cool slowly in the air for at least 20 minutes. Do not cool it with water. Do not put it in the refrigerator. Do not blow on it. Slow cooling is what allows the outer black Cu₂O layer to detach due to differential thermal contraction, leaving exposed the reddish Cu₂O layer, which is the photovoltaic semiconductor you need. If you cool it quickly, the black layer sticks, and the cell does not work. Third, once it is cool, gently rub it with your fingers under running water to remove the loose black oxide residues. Do not scrub hard. Do not use a scouring pad. Only remove what comes off on its own. What remains attached and reddish in color is your active layer. Fourth, prepare the electrolyte. Dissolve 2 tablespoons of salt in a glass of water until no more salt dissolves. This is the saturated solution that will act as the ionic bridge between the 2 copper plates. Fifth, place both copper plates inside the plastic container without them touching each other. The oxidized plate is the positive electrode. The clean, unoxidized plate is the negative electrode. Attach each one with an alligator clip connected to its respective wire and pour in the salt solution until the plates are partially covered, leaving the edges with the clips outside the liquid. Sixth, expose the setup to direct sunlight or a powerful lamp. Connect the multimeter between the 2 wires. Select the microampere or milliampere scale. If everything is correct, you will see a reading. It may be small, between 10 and 100 microamperes, depending on the quality of the oxidation and the intensity of the light, but it will be there. That is electricity generated by sunlight through kitchen materials. If you made it this far, this content deserves a like. Share it with someone who believes solar energy always has to be expensive, and snort subscribe. What's coming in the next videos is even more useful. I'll be direct with you because the respect I have for you does not allow me to exaggerate. A cell of this size generates very small amounts of electricity on the order of microamps. You're not going to charge your phone with it, at least not with a single cell the size of your hand. But that does not mean the knowledge is useless. It means it has to be scaled correctly. By connecting several cells in series, their voltages add up. By connecting them in parallel, their current adds up. With a battery of 20 oxidized copper cells, the size of an A4 sheet each, under the right light and electrolyte conditions, you can generate enough current to power low-consumption sensors, small LEDs, or button battery chargers. There are documented projects in maker communities that have used this principle to power remote environmental monitors in areas without access to the electrical grid. The real value of this experiment is not how much electricity it produces today. It is what it proves to you, that solar energy is not the intellectual property of any multinational corporation, that the principle powering a $500,000 installation is the same principle. You can reproduce with a copper sheet and vinegar. That changes the way you think about energy, about technological dependence, about what you truly need to buy and what you have simply been convinced that you need. The engineers who work in renewable energy have known this experiment since their first year in university. Solar installation technicians have done it in class. The difference between them and you until today was simply that nobody had explained it to you in terms that invited you to try it this afternoon. The first practical photovoltaic device was built in 1883 by Charles Fritz, an American inventor who coated selenium with a thin layer of gold and achieved an efficiency of 1%. It was ridiculously inefficient by today's standards. It was also functional. It demonstrated the principle, and it cost a fraction of what an equivalent modern panel would cost. In 1954, Bell Laboratories developed the first silicon solar cell with an efficiency of 6%. Time magazine called it the beginning of a new era. 7 decades later, the technology has improved enormously in efficiency, but the business model has ensured that access remains expensive and dependent on industrial manufacturers. Homemade copper oxide cells are, in spirit, much closer to Fritz's work than to highly pure doped silicon panels. And Fritz worked in his workshop with the tools he had on hand, with the conviction that sunlight should be convertible into useful energy without the need for entire factories. That conviction is still valid. Physics has not changed. What has changed is who has an interest in making sure you remember it. I know there are people watching this who are thinking about emergency preparedness, educational projects with their children, reducing, even symbolically, their dependence on the electrical grid, or simply understanding better how the world around them works. All of those reasons are valid. All of them lead to the same place: the conviction that practical knowledge is a form of freedom. This device is not going to solve the energy crisis, but it is going to prove something that no electric company wants you to internalize: that solar energy, in its most elementary form, is within reach of anyone who understands the principle and has a free afternoon. That is not a small thing. The materials list is in the video description. The steps are in the pinned community video. If you do the experiment, share the result in the comments. I care about knowing what readings you are getting, under what lighting conditions, with what electrolyte variations. That is what turns this into a real community and not just another passive consumption channel. Subscribe if you still haven't done it. Share this video with whoever you think needs to see it, and leave a like. It is the fastest way to tell the algorithm that this kind of content deserves to reach more people. See you in the next one.